what if you only had to guess half a word? Shuffle any word's letters, then build the smallest palindrome bigger than where you started. It sounds like checking millions of arrangements, but a palindrome only needs half its letters decided. That's the whole game today. Kai finds a spot for it in the front rank. But there's a twist. The letters have to snap back into a perfect mirror image word. Given a scrambled word and a target word, he wants to rearrange those exact letters into the smallest palindrome he can make that still beats the target alphabetically. If the letters just won't cooperate to form any such palindrome, he comes back empty-handed. This is LeetCode 3734, lexicographically smallest palindromic permutation, greater than target. I'm Kai. Welcome back to Fun with Learning Technology. We're given two strings S and target, both the same length. We need to rearrange the letters of S into a palindrome. Reads the same forwards and backwards. And among every palindrome we could build from those letters, find the smallest one that's still strictly bigger than target. If no arrangement of S can beat target, we return an empty string. Look at S equals B, A, B, A, and target equals A, B, B, A. There are two A's and two B's, both even counts, so a palindrome is actually possible. The left half only needs one A and one B. Matching target's left half exactly gives you A, B, B, A, but that ties target instead of beating it, so you bump the left half up to B, A, mirror it, and land on B, A, A, B. The length only goes up to 300, so we don't need anything fancy. Counting letters and building one half of the string is plenty fast. And since it's only lowercase letters, we're always working with at most 26 buckets, which makes counting frequencies cheap and simple. Take our actual letters BABA. By hand, that's only 6 arrangements to check, but S can be up to 300 letters long. Just to feel the scale, 10 distinct letters alone would already be past 3 million arrangements. 300 is past anything we could ever brute force. Here's the trick. A palindrome mirrors itself. Once you pick the left half, the right half is forced. It's just the reverse. So really, we're not arranging the whole string. We're only deciding half of it. The trap people fall into. If your left half ties with target's left half, they stop and assume it's fine. But the mirrored right half still has to beat target's real right half, and it might not. First, count how many times each letter appears. For a palindrome to exist at all, at most one letter can have an odd count. That odd one out, if it exists, sits alone in the dead center. Everything else splits evenly between the two mirrored halves. Now greater than the targets, what does that actually mean here? Because of the mirror, the left half decides the comparison almost every time. Wherever it differs from target's left half, that settles it. The one catch, if our left half matches target's exactly, target itself might not be a palindrome, so we'd still need to check the full string. So the real question becomes, what's the smallest valid left half that beats target's left half, or ties it and still edges past target overall? We build the left half left to right, trying to match the target exactly. The moment we can't match, we ask, is there a bigger letter available here? If yes, place the smallest one that's still bigger, then fill everything after it as small as possible. That's how you guarantee the result is the smallest one that's still bigger. But what if you reach the end and never found a spot to increase? Then you back up one position and try to bump it there instead. It's exactly like carrying a digit when you add one to a number. If you run out of positions entirely, no answer exists. This part counts the letters, bails out early if more than one has an odd count, and splits the counts in half for building just one side of the palindrome. This loop matches target's left half as far as it can, saving a snapshot of the remaining letters at every position. So if we need to backtrack later, we know exactly what was available at each spot. Let's put the whole thing together. We start by counting every letter in S, and if more than one letter has an odd count, there is no palindrome to build at all. So we return empty right away. Otherwise, we grab that one odd letter as our middle character, figure out how many positions the left half needs, and cut those counts in half since the right half will just mirror it. We also slice out target's own left half since that's what we're really racing against. Two small helpers come next. Fits checks whether a word can be built from a pile of letter counts, and smallest just lays out whatever letters are left in sorted order, which is always the smallest possible arrangement of them. First we try the exact match. If target's left half can be built from our letters, rebuild it, mirror it, and check if the whole palindrome actually beats target. Sometimes it ties instead of winning, so that's not automatically the answer. If the exact match doesn't work or isn't enough, we fall into the greedy search. We walk through target's left half position by position, matching it exactly as long as we have the letters, and saving a snapshot of what was left at every step along the way. Once we hit a position where we can't match anymore, or we match the whole thing without ever beating target, we walk backward from that point, position by position, asking at each one, is there a letter available here that's bigger than what target has? The first position where the answer is yes, we place the smallest letter that still beats target there, fill everything after it with the smallest letters remaining, and that's our new left half. Mirror it, drop the middle letter in if there is one, and return the result. If we walk all the way back to the start and never find a spot to bump, there is genuinely no answer, so we return empty. The exact match branch exists because matching target's left half exactly doesn't guarantee winning. It can tie, and only checking the build palindrome against the full target catches that. The backtrack loop is really just trying every possible carry position, from the point of failure back to the very start, and taking the first one that works. Remember our letters from the start. Count them, take half, greedily push past the target, mirror it back. That's the whole algorithm. No brute force. No wasted work. The mirror trick isn't just for palindromes. Anytime a structure forces one half of a decision to fix the other half, anagram checks, mirrored strings, symmetric matrices, counting letters or values, beats, generating every arrangement. Talk is cheap. Let's actually run this. I fed it all 4 of the problems, real examples. No cherry picking plus 3 extra edge cases I picked myself. Let's actually time both on a real 10 element input. Brute force took 361.78 milliseconds. The optimal version took 3.48 milliseconds. That's a real 1032x from actually running both just now, not a complexity estimate. Here's one for you. If the target has odd length but every single letter shows up an even number of times, can you still form a palindromic permutation? Pause and guess before I answer. Think about what an odd length palindrome actually needs in the middle. No, it's impossible. An odd length palindrome needs exactly one letter with an odd count to sit in the middle. If every count is even, there's nothing to put there. Second one, our greedy approach fills positions from the left, picking the smallest valid letter each time. Why can't we just sort every letter and mirror the sorted string instead? Take a second to think it through. Remember what greater than target actually forces us to check, because plain sorting only gives the smallest palindrome overall. It ignores the greater than target constraint. Greedy has to sometimes choose a bigger letter to stay above the target and backtrack if that choice paints it into a corner. That's the smallest palindromic permutation, strictly greater than the target. The trick was counting letters instead of arranging them, then greedily placing the tightest valid mirrored pair at each position, backtracking to a loser choice when no letter works. Its own work with a constant 26 letter scan at each step.